In this video, we are going to be talking about something called the Chatelier's Principle, which we will have a lab on this semester, so yeah, this will be kind of important. So I'm going to read this statement, then I'm going to kind of broad terms try to talk about what this is. This is less of a calculation idea, and this is more of something big picture, like how does equilibrium work and how can you change things. So Le Chatelier's Principle, some textbooks phrase it a little differently, but it's basically this. When you have any change in concentration, pressure, volume, or temperature that is imposed on a system that is at equilibrium, so in other words, we're starting at equilibrium and then we're messing with it. Okay, we're heating it up, we're cooling it down, we're changing the pressure, something, adding stuff, adding reactants or products. The system is going to respond by getting a new equilibrium condition that minimizes the impact of that change. Okay, so what we are going to do is we're going to talk about each of these things in turn. Okay, actually, pressure and volume are kind of connected, so we're just going to talk about that all at once. But what we're looking at is if you have a system at equilibrium, so you've got reactants and products, and there's a balance, like a Kc value tells you the ratio of products to reactants raised to the coefficients. If you change something, change the amount of reactants, change the amount of products, change the overall pressure of the system, change the temperature, you've now messed with that balance, and it's going to have to get back to that same ratio by shifting concentrations around. Usually what this means is it's either going to have to shift to the left to create more reactants or shift to the right to create more products. Those are like the two main options. Okay, so let's talk about concentration first. I'm going to kind of talk about this in broad terms, like generalized terms, because it works pretty well actually. So let's say we've got A plus B forms C plus D. Okay. If there was an equilibrium constant, it would be products over reactants raised to the coefficients, but none of these have coefficients, so it all works out pretty easily. Okay. But what this means is that if we're starting at equilibrium, if we change any of these things, we're basically visualize it like a balance. If we have a specific amount of reactants and products that give us this equilibrium constant. If we increase the reactants or increase the products or decrease the reactants or decrease the products, we've now upset the balance, and it's going to have to shift. Like if you remove reactants, it'll have to, the side will get lighter. You'll have to shift things to the left to like make up for it. So let's kind of look at specific examples and just see how this goes. So let's say we increase one of the reactants. Increase concentration of A. So what we're saying is if you're starting at equilibrium and all of a sudden, you've got a well-balanced system, a specific concentration of A and B and C and D, and everything's at equilibrium, and you just dump in whatever this compound A is, dump in some more. The concentration's going to go up, right? Which means you will not be balanced. There's a couple ways to think of it. Oops. So one option is reactants, products, and it's like a balance. Kc does not have to be, it could be balanced like this, however the thing decides to, but we're going to visualize it like this. If you add more A, you have more reactants. To make this thing level out, you're going to have to shift to create more products, right? To make this get back to level. That is one way to think through it, and that's literally how I visualize it. The other logic is it's a ratio, and if you increase this number, increase the bottom number, your number is too small, so you have to create products to make the numerator bigger to get back to Kc. So the overall result is if you throw reactants in, it's going to shift to the right. I usually indicate it with arrows. Some textbooks or like Sapling might indicate it as like shifts towards products. But it's pretty easy, right? If you have reactants and if you add A or B, if you add reactants, it's going to shift to the right. Okay. If you increase whatever this compound C is, if you add some products, basically the opposite's going to happen. Trying to not color over my hand. Say we're balanced and you add more of the products, it's going to shift this way. You're going to have the reverse reaction happen more to get more reactants to balance it back out. Similarly, you could visualize it as if you add more C, the numerator is getting bigger, so you're going to have to shift to the left to make the denominator bigger to get it back to that original ratio. So basically, if you add products, it shifts to the left. Not too bad, right? Similarly, if you remove one of these things, so let's say we remove some of B, okay? Well, if you have reactants on this side and products on this side, this is balanced. If you start removing reactants, this side's gonna have less, so this side will start weighing more. My metaphor only goes so far, or my analogy only goes so far. So it'd have to start shifting to the left to get that balanced again. Similarly, if you lowered the value of the denominator by removing reactants, you're gonna have to lower the numerator to make this balance out, to get it back to what it was. So basically also shifts left. So honestly, here's the big picture. If these are gases or aqueous, we'll deal with what happens if they're not here in a little bit, but if these are gases or aqueous, if you add reactants, it shifts to the right. If you add products, it shifts to the left. If you remove reactants, it shifts to the left to make up that loss. If you remove products, it shifts to the right to make up that loss. That's the entire concept. Okay? I guess let's talk about pressure and volume. So pressure and volume are related, and they really only apply to things that have gases in the equation. They don't all have to be gases. Like not all the compounds in the balanced equation have to be gases, but there have to be gases somewhere in the thing. Okay. We talked about the gas laws last semester, right at the end. The idea is if you have let's say you have a balloon and you crush it, so the volume goes down, what's happening is the molecules inside are experiencing an increase in pressure. So basically, volume and pressure are kind of opposites as far as we're concerned. If pressure goes up, volume goes down. If volume goes up, pressure goes down. So I'm going to kind of talk about them together because they're all kind of one concept. So if you have a system at equilibrium and you crush it, basically increase the pressure. So when the external pressure is increased, which is the same thing as the volume decreased, the equilibrium will shift toward the side with the fewest moles of gas. So this only affects gas particles. The opposite of this is also true. I don't know why I made that line so long, whatever. So if you decrease the pressure, it'll shift to the side with more moles of gas. All of this only matters if there are gases in the balanced equation. Or gases in the reaction, I suppose. Okay. This one's pretty straightforward, honestly. Let's look at an example. So let's say, I think we saw this reaction at some point in one of these videos. N2O4 is a pretty unstable molecule. It falls apart and forms two NO2 gas molecules. This thing is fairly reactive and it will also go backwards. So depending on the conditions, temperature, pressure, whatever, you can control which one you've got. So let's say we increased the pressure overall. So like we had this thing at equilibrium and we just crushed it. We increased the overall amount of pressure. We want to know which way is it going to shift. Well, literally all you do is count up how many moles of gas there are on each side. This side has 1 mole of gas, and this side has 2 moles of gas. So if you increase the pressure, it will shift to the side with fewer moles of gas. So it should shift to the left. Okay. If you increased the volume, so say it was in a container and you expanded the volume and it was sealed up so the pressure changed with it. Increasing the volume is the same thing as decreasing the pressure. So it should shift to the side with more moles of gas. Basically, there's more space for these moles of gas to exist, so the more space you give it, the more of these you're going to get. That's the entire concept. This isn't real tough. Okay, I want to look at another example real fast. It's kind of the last two things combined. So I may have mentioned this example earlier in this chapter, but that's okay. We haven't seen it in this context. So let's say we've got this equilibrium. So everything's at equilibrium, it's going to do what it's going to do. We want to know what happens if we increase the amount of CaCO3. Now, the previous thing said that basically for concentration, if you increase reactants, it shifts towards products. If you increase products, it shifts towards reactants. This is the one exception. This is a solid, and solids are not part of the equilibrium constant. We talked about that a couple videos ago. So there would literally be no change. Okay. If we increased the CO2, that actually is one of the ones that's part of the equilibrium constant because gases and aqueous things are. So you'll be increasing products, so it would shift to the left. If we increased the pressure, well, on this side of the equation, there is 1 mole of gas. There's 2 molecules, but only one of them's a gas. 1 mole of gas. And on this side, there's 0 moles of gas. So it's gonna shift to the side with fewer moles of gas because you increase the pressure, which is the left, which is none. Okay? Little weird, but the idea is if you have a liquid or a solid in the balanced equation and you changing its concentration has no impact on Chatelier Principle. It is part of the balanced equation, but it doesn't affect the equilibrium because these things are not part of the equilibrium constant. Okay? All right, let's talk about temperature. Get done with this. Okay. Temperature, the easiest way to think through it is to literally think of it as a reactant or a product. So, if delta H is negative, basically the reaction is exothermic. It heats up as it goes. Essentially what that means is it's producing heat. We can visualize heat as a product. So we can just treat it as a product. We don't usually write it in the balanced equation, but for visualization's sake, for what we're talking about here, we could. So let's say we had some generic reaction, A plus B, or A in equilibrium with B, whatever the compounds are. And we have, looked up that the delta H for this reaction is negative, okay? What that means for us is we can take this and interpret this as saying that heat is a product. And then literally when you increase or decrease the temperature, you just visualize it like you do the concentration rules. So if we increase the temperature, what we're doing is adding more heat, which is a product, it'll shift to the left. If we decrease the temperature, you're removing a product, it's going to shift to the right. Okay? The opposite of this is also true, and I'm just going to write it down so it's in your notes. But if delta H is positive, basically endothermic, you have to pump heat into it to make the reaction go. Basically, you're treating heat as a reactant. So everything kind of shifts. So let's say switch the letters here. C equilibrium with D. Doesn't matter what these compounds are. And delta H is positive. Okay, endothermic. Okay, so because this is positive, this means we can treat heat as a reactant. So now, when you increase the temperature, basically adding a reactant, so it'll shift to the right. If you decrease the temperature, you're removing a reactant, so it'll shift to the left to make up that loss. Temperature's not too hard, right? As long as you remember that exothermic means heat's a product and endothermic means heat's a reactant, that's literally, you can just treat it like the other set of rules we did a couple pages ago. Okay. Now, I will say this does point out a little bit of kind of a catch-22 with reactions. So we talked about in the previous chapter that there's an activation energy, amount of energy that you have to put in to make a reaction go. Okay. So for an exothermic reaction, you have to put in a minimum amount of heat to get from A to B. But anything more than that is actually going to slow down the reaction. It's going to make it go to the left. Like if you're trying to make B, adding heat's actually going to shift it back to the left. So there's like a fine line of how much heat you can add. Endothermic reactions are easy. You need there's an activation energy to get from here to here, and you have to pump heat to make it go to the right. You can just set this damn thing on fire and it'll go to the right. Okay. The last weird little one that we hadn't mentioned yet, that wasn't on the initial list, is the idea of catalysts. Like, how does that affect equilibrium? We talked about catalysts in the last chapter. There's something that is added that starts out as a reactant, gets used up, and comes back as a product, and it increases the speed of the reaction by lowering the activation energy. It turns out that a catalyst speeds up the reaction. So it gets to equilibrium faster. So if you have something that's in equilibrium and you have a catalyst present, if it's not at equilibrium, it will get to equilibrium a whole lot faster. But once you're at equilibrium, it doesn't affect the equilibrium at all. Okay, so kind of a little weird, like, it seems like it should make a difference, but it doesn't. Basically, once you are at equilibrium, you could add a catalyst in and it won't affect anything, even if it seems like it should speed up the reaction. Sorry, realizing this pen is making my handwriting look a little sloppy. All right, so before I quit this video, let's try one more example that's kind of got everything mixed into it. So this is page 16, I guess. Sorry, just trying to keep myself straight. So let's say we have compound A, which is a gas, plus 2 moles of compound B, which is aqueous, in equilibrium with 2 moles of compound C, which is a gas, and we have a delta H equal to -1 or 7.51 kilojoules per mole. Doesn't even matter what this compound is, doesn't matter what anything's going on. So what we want to know is, we're going to deal with all of the variables at once here. So we want to know if we were already at equilibrium and you increase the concentration of B, is this going to shift to the left, to the right, or is there going to be no change? Those are pretty much always the options. Okay. So because this is aqueous, it's not a liquid or a solid, if you increase reactants, it should shift to the right. What happens if we cool everything? Basically decrease the temperature. Sorry, my handwriting got bad there. Well, because this is a negative delta H, it is exothermic, we can visualize this as heat being a product. So if we cool the system, we are removing products, so we're going to have to shift to the right to make up the difference. Okay. What happens if we increase the pressure? I'm going to switch colors here because I only want to scribble on this so much. If we increase the pressure, what we're looking at is number of moles of gas. So the aqueous thing has no bearing on this whatsoever, but on this side of the reaction, there is 1 mole of gas, and on this side, there is 2 moles of gas. So if you increase the pressure, it's going to go to the side with the fewest moles of gas. So it should shift to the left because there's only 1 mole of gas on this side. What happens if we remove compound C? So suppose we have find a way to like just remove just that. Okay, maybe react it with something else. Basically pull it out of reaction. Well, it's not liquid or solid, so if you're removing a product, it should shift to the right. what happens if we add Nh3 liquid as a catalyst? Basically, if you add a catalyst, if it's already at equilibrium, you will get no change. Okay. I will tell you that in the real world, if you can understand the basics of this, you can, and you work for like, a pharmaceutical company, we're trying to increase yields. So suppose you've got this reaction and like, this is the product you're trying to make. What set of conditions would be ideal to make this happen? Well, you would want as high of a starting concentration of both of these as possible. You would want the system as cool as possible with still enough energy to get over the activation energy. You'd want as high of a pressure as possible because low pressures make it go to the left. And you'd also want to be able to remove C as you go. Catalyst probably wouldn't affect anything. Might make it faster to, like once it does get, like once you mess with it to get back to equilibrium, it might speed it up. But so essentially for this reaction, we want lots of reactants, cold system, high pressure, and being able to remove product all at once. And you could increase your yield of this by quite a lot, all based on the Chatelier's principle. All right, thank you.